Today's topic is about tactility of a keypad. My name is Thomas, and I'm the team leader for our design and development department here at Mikroprint. Please write questions during the presentation, and we will answer these at the end of the webinar. So, tactility is often difficult to define with numbers and facts. It's often defined as a feeling or with a comparison to a physical sample. And even with the reference sample, it's discussed as what do you feel and what do you think. We often receive quite vague tactile button specifications from customers, such as we want a good tactile or haptic feedback, or we simply just want a good click, or a specific activation force of, for example, 3.5 newtons. So we wanted to explore this dilemma some more, and we found a way to make it easier for us internally and for our customers to specify the tactility of a keypad. So we started out by making a lot of different measurements and studies of existing keypads that we have in-house. We discovered and defined a set of factors relevant to look at when defining the click of a button. These factors make up what we call the tactility of a keypad. And this is what I would like to share with you today. So for the next 20 minutes, I'll go through these points. Why is tactility important? How to specify tactility, and how to translate customer requirements into tactility specifications. So, tactility is an important part of the user experience. It's essential for good and safe operation of a device, but it's also an important part of the overall user experience and user satisfaction. But it's important also to say when talking user experience, it's worth mentioning that tactility is just one of these factors. The physical feel of a button is also defined by the materials and shapes. The design and shape of a button also have a big impact on tactility, but this is a topic on its own. And of course, we also have colors and backlighting of a keypad that creates the visual feedback. But today, we're going to focus on tactility. So, let's have a look at how to specify tactility. Based on a large number of measurements as assessment of existing keypads as mentioned, we identified these 4 variables that makes up tactility. They are equally important, but also dependent on each other. The first one is force. This is the feeling of resistance when pushing down the button. And the second is snap ratio, which is the change in the feeling of resistance when pushing the button. And then we have travel, which is simply the movement of the button before activation. And last but not least, we have audio, which is the sound provided by the click. But before we dive into these 4 tactility factors, let's have a look at what actually makes the click. First, we have metal domes. This is widely used in both silicon and membrane keypads, and is ideal for thin keypad constructions when this is a requirement. Next, we have tactile switches, which is used in both silicon and membrane keypads. It's suitable for keypad constructions where you have PCBAs. Then we have carbon pills, which is a click specific for silicon keypads. It is actually molded or screen printed or glued together with the silicon actuation pin on the underside of the keypad button. And finally, we have polydomes, which is a specific click from membrane keypads. The click is actually made by an underlaying embossed foil material. So let's have a look at the first tactility factor. And this is the one we call force. It's expressed in newtons and explains how much force a button requires to be activated. Polydomes, as you see here, offer the forces in the lower end from 0.5 to 2 newtons, and metal domes offer the widest range of force from 0.5 all the way up to 20 newtons. So a key takeaway from this for you to remember is that the higher the newton value, the more force you need to activate a button. For example, high activation force can, example, be used for emergency stop buttons or to avoid misactivation of a button. And low force could be used for ergonomic purposes, for a keypad where you have a lot of actuations during the operation of the keypad in daily use. The second tactility factor is travel. It's expressed in millimeters, and it simply shows how far you need to push the button before reaching activation. And as you can see here, we visualized a silicon keypad with a carbon pill, which offer the possibility for a longer travel, where you're a bit more limited when looking at membrane keypad constructions, where they only offer travels in the lower end. But it's also important to say that it's from a UX point of view, it's not good with too long a travel or too short a travel. So you don't want too long a travel where you have to feel you're pushing the button for too long without actually reaching a point where you feel it's being activated. But you also don't want too short travel where you barely have to touch the key before it activates. So it's a balance between these two. But sometimes the keypad construction or the product assembly may require either a long or a short travel. So for you to remember is that the higher travel, the longer the movement of the button, and obviously the shorter travel, the shorter movement of the button. The third tactility factor is snap ratio. It's expressed in Newton across millimeters, and it explains the relation between force and travel. It explains and shows how much you actually have to push the button, as visualized here, before you reach a point where the key snaps and makes contact with the underlying circuit. This specific part of the curve also visualizes how big a click you feel when pushing the button. This shows that force and travel goes hand in hand. It might be a bit theoretical, but most important for you to remember is that the steeper the curve or the steeper the drop you have here, the higher clicker feedback, and the softer the curve or the less steep curve you have here, the lower the click feedback. This curve is the most important tool to visualize and measure the feel of a button. And this is also the area that we focused on in our measurements to confirm the data in our studies. And last but not least, we have audio, which is actually a bit of a joker when talking tactile feeling, as it influences the sense of hearing and not the sense of feeling. But this is something that affects the tactility feedback experience as well. It's expressed in decibel, and as you can see here and visualize on this curve, from the carbon pill can offer decibel in the lower end, where metal domes offer the audio feedback in the higher range. So the rule of thumb is also to remember that activation force and audio goes hand in hand, where high activation force also creates high audio feedback, for example, with a metal dome. And low activation force creates low audio feedback, for example, with a keypad construction with a carbon pill. So now let's have a look at how this knowledge can be used in practice. I'll go through some typical scenarios of how a customer brief could be translated into tactility solutions. So one of the first scenarios could be a keypad for an industrial tool with a good click. So we could say here that the brief from the customer could be that it's used on a construction site, it's operated with gloves. So we translated this into that we need a level button design, so it's easy to feel the key when operated with gloves. And we knew in order to make this level button design, we have to look at a silicon keypad. So here we know that we want either to use a metal dome, tactile switch, or the carbon pill as a part of the silicon keypad. The next brief from the customer was simply could be that they wanted a good click. And we translated this into we wanted high audio feedback, we wanted high activation force, and we wanted a high snap ratio to really feel when the button has been activated. So we had to outrule the carbon pill here and look at tactile switches and metal domes. And the last requirement could be that it's a front-mounted keypad into a plastic housing with a recess of 2 millimeters. So we translated this into that we needed metal domes because, as mentioned earlier, we know that metal domes is widely used for a thin keypad construction. So we needed to do that in order to fulfill this requirement. A second scenario could be a keypad for medical devices with good ergonomics. The brief from the customer could be that it's used in a medical environment and we want it to be easy to clean. So we translated this into that we wanted to use or design a membrane switch keypad with embossed keys because we wanted still to be able to feel the keys with the embossing, but not too much level design because that would affect the cleanability of it. So we outruled the carbon pill here as part of the silicon keypad and continue with polydomes, tactile switches, and metal domes. Then the other requirement was that it was a precision controlling and they had a high number of actuations during daily operation. So we translated this into that we wanted low activation force, below 200 grams, and we wanted a mid-snap ratio, just to be able to feel that it's activated, but not too high. So here we continue with the polydomes and the metal domes. And the last requirement was that they wanted 1 million plus key activations in a high temperature and moist environment. So we translated this into that we needed a metal dome with 1 million plus activations because we know that polydomes are not very suitable in high temperature or moist environments and most commonly cannot withstand the 1 million activations. The last scenario could be that there's a large distance between the keypad on the front side and the PCB on the back side with the circuit layer. And as the brief from the customer could be that there is this long distance from the actual front side to where we need to interact on the back side inside the housing on the electrical layer. So we translated this into that we needed a long travel. We needed a long actuation pin to reach the top side of the keypad all the way down to the circuitry layer. So we knew we either had to look at a tactile switch with a very long actuation pin, or we could look into designing a longer key or higher key or a longer actuation pin on the backside of a silicon keypad. Then they also wanted low audio feedback, so low noise. So we knew that a tactile switch normally makes this click from the snap ratio. And we know that there's a possibility in designing this into a carbon pill solution with making a low noise click. So that's why we continued with the carbon pill solution. So to sum up, this webinar is our attempt to make it easy for us and for you to design good tactile feedback. It can be a dialogue tool to connect data with feelings as we did in our internal studies, trying to measure first what do you actually feel and then connecting that to some data with some measurements afterwards to confirm that our feeling actually can be backed up by the data that we made. It's also to have something more specific than a feeling when talking a good click. But it's also important to say that tactile feedback cannot only be data-driven, it's still case-specific and it requires dialogue. And it's a balance between these tactility factors of force, snap ratio, travel, and audio. And as mentioned, very case-specific, so you need to balance these very carefully to come up with the best solution specific for your product. So before we go to your questions, we have one question for you actually. We've just been through tactility as one of the aspects of user experience, but we balance between other areas when developing HMIs together with you. So what's next? What would you prefer to hear about next time? Oh, okay. Oh, sorry. There we go. Oh, the shaping of the buttons. Okay. Well, I guess you're pretty agree on what you want to hear about. Okay, interesting. Thanks. Should we show the results? No. Okay. Let's go to the Q&A. We have some questions here. Yeah, something about sharing the PDF presentation. Of course, yes, sure. That's already been answered. Yeah. So we have a question here. How do you see touchscreen and tactility requirements? Yeah, that's a thing. You know, touchscreens are being used very much. Also becoming more commonly used in also for industrial application, where that was more from a consumer point of view. These were being used. But we see more and more the integration actually between, it's not only just a touchscreen or a silicon keypad, for example, but it's a combination of these two. So we see that you get the good tactile feedback for a silicon keypad with all of the good factors that I just talked about. So you have for the most important, for a nav key or for a select key or whatever, you have that on and off button. You have that as a physical button that provides this good tactile feedback. And then you have on the touchscreen the other features that maybe are not that important and not being used in a daily operation, but something that has this flexibility in doing it interactive also. So we actually see more and more of these combinations of touchscreens and physical keys, which is also an exciting combination to work with from a design point of view. Yeah. Yeah. Any other questions? Really? Okay. Well, I think that's more or less it. Thanks for your time and thanks for listening. You also feel free to contact us afterwards if you have any questions regarding what I guess you maybe want to see the presentation again, and maybe it's a lot of information, so maybe you need to read it again to let it sink in. And then maybe if you have any questions when seeing it again, please do not hesitate to contact us, and we'll try our best to answer your questions. Yeah. So thanks for now. Have a great day, and thanks for your time.